So we were discussing the 2 to the power k factorial design yesterday when we stopped. I think we talked about the theory, and today we'll look at a problem. So are you able to see my screen?
Oh, yes, sir.
Okay. So I had already written part of the question. So we are going to look at 2 to the power k factorial design. So the question is, you are talking about the heat sink, which is used to cool down a CPU processor. The heat sink has 2 important parameters: the number of fins, that is designated by X subscript A, and the second parameter is base thickness, which is designated as X subscript B. And these 2 parameters are assigned values +1 and -1 depending on the high or low values respectively. The outcome of these 2 parameters are in terms of the cooling efficiency, which is represented in terms of the heat transfer coefficient, and that is the variable y in this case, and that has a value between and 10, 1 being the worst and 10 being the best. And we do a 2 to the power 2 factorial design, a 2 to the power 2 factorial experiment was performed. That means you first vary the 2 parameters between the extremes, low and high for both of these, and then you noted down the results. So that is basically your 2 to the power 2 factorial experiment. And the following matrix gives the results of the preliminary experiments. The following matrix gives the results of the experiments. So this is the result. So you have XA parameter in this direction, XB in this direction. So XA can have +1, -1. Similarly, XB can have +1 and -1. So when XA is +1, XB is +1, you get a value 2. When XA is +1, XB is -1, you got a value 8.2. When XA is -1, XB is +1, you got a value 1.5. And when both are low, you get a value of 3.5. So this is the table. Now, the question is, you have to determine the regression parameters. And comment on the results. Okay. So let us First, write down the regression equation that yesterday we had talked about. So typically the equation is y equal to P naught plus PA XA.
So can you go to the page before?
Yes.
Hello?
Yes. Yeah.
Sir, I think some of them are sitting in a room and the speakers were on at once. So the mic.
Yeah, so can you go to the page before for 2 seconds? We didn't finish writing.
Okay. Yeah, please do.
Thank you, sir.
Okay. So this is the equation I had written down yesterday. We have PAB, say, into XB. So today you have the preliminary results for this equation, right? So this is basically your y1, this is y2, this is y3, this is y4. So you can actually get the equations. So you have P naught plus PA plus PB when XA and XB are both 1 plus PAB will be equal to 2. That is the first one here. This one. And then you talk about PA is minus 1 and XA is minus 1 and XB is plus 1. Then XA is minus 1 and XB is plus 1. You have P naught minus PA plus PB minus PAB, because 1 is plus, 1 is minus, so the product will be negative. This is equal to 1.5. Then P naught plus PA, then minus PB minus PAB will be equal to 8.2. You see here, this is 8.2, and so this is basically your 8.2. And when both are negative, so P naught minus PA minus PB plus PAB equal to 3.5. Okay. So yesterday, the way we solved it, you just follow the same procedure. And if you add all the equation, you can actually say P naught is 2 plus 1.5 plus 8.2 plus 3.5. All the terms on the left hand side will get cancelled. Only 4 P naught will be there. So divide by 4, you get P naught. That is 15.2 by 4. That will be 3.8. And once you know P naught, for example, if you take this equation and add them up, then you will get 2 P naught plus 2 PA plus PB minus PB will get cancelled, plus PAB minus PAB will get cancelled. So this will be equal to 8.2 plus 8.2. So that is 10.2. Right? Already you know P naught. So that is 2 into 3.8 plus 2PA is 10.2. So from here you can find PA is basically 1.3. Okay, so this is 7.6, 10.2 minus 7.6 is basically 2.6, and divided by 2 will give you 1.3. Similarly, if you add these two equations, you can show that 2P0 plus 2PV equal to 3.5. So you substitute for P0, that is 3.8, and you can find PV will be equal to minus 2.05. Okay. Similarly, if you add the first and the fourth equation, you can get to P0 plus 2PAB is 5.5. Substitute for P0, so you can find PAB is basically minus 1.05. So you have all the regression constants determined. So P0 also you have found 3.8. So everything is, so you have the equation y equal to 3.8 plus 1.3 xa minus 2.05 xb minus 1.05 x into xb. Now, we want to find out between number of fins and base thickness, which parameter is more dominant, or both parameters are equally dominant, as well as the simultaneous variation of the number of fins and base thickness. That means the interaction effects. So we want to know whether we can really, we have to vary this number of fins successively in gradually from a low to high, or number of fins doesn't have any much effect as compared to base thickness, or vice versa. So we need to really find out what I said yesterday, the square of the deviation of the individual y from the mean, that is P0. Okay, and then we can decide which effects are dominant. Okay, so if you find out the sum of square of deviation, squares of deviations, basically sum of yi, these are yi's, y1, y2, y3, and y4, minus y mean, which is y1 plus y2 plus y3 plus y4 divided by 4. This is nothing but your P0 here, right? Square of that. Now, I can write this as, so I have, if I rearrange this, okay, I can actually show that the sum of squares of deviation. So I leave it to you as a homework. You can do this for yourself. This will be equal to 4 times PA square plus PV square plus PAV square. Okay. So this, if you find out PA, PB and PAB, this will give you, if you just substitute there, this will give you 27.98. So really, the values of PAV square, PB square and PAV square would determine which effects are dominant. Okay, so we need to really find out the sum of squares of deviation coming from XA. Okay, so that is basically 4 into PA square, and PA already you know, so this will be 6.76. Similarly, sum of square of deviation coming from XB is 4 PB square. That will come out to be, PB already is here. So if you just substitute, you get 16.81. Similarly, sum of square of deviation of the interaction effect, that is XA, XB, is 4 times PAB. So that will give you 4.41. So out of total 27.98, 6.76 coming from A, 16.81 coming from B, and 4.41 coming from the interaction effects. So if I can now put them in a tabular form, I make a table. So this is SD, that is sum square of deviation. I write the contribution, percentage contribution. The total is 27.98, which is basically 100%. Out of that, SSD coming from XA is 6.76, and that is 24.16%. You divide 6.76 by 27/98 into 100, so that will give you 24.16%. Similarly, SSD coming from XB, the second parameter, 16.81, this is 60.08%. Then the interaction effect will be coming from XA, XB is 4.41, that is 15.76%. So as you see here, nothing is really negligible. Okay, so if something is, let's say, 1% or less, you would say that the contribution is negligible. Since all these three are non-negligible, you basically conclude that all the factors have to be evaluated at all the levels. Okay, so all the parameters, that is the number of pins, its thickness, and simultaneous variation of variations of both number of pins and base thickness. That talks about the interaction effect. Are important. So you need to really do a full factorial design here. That means all the different parameters, there's a number of pins starting from 5, 10, 15, 20, everything you have to vary in the experiment. Base thickness, 2 millimeter, 3 millimeter, 4 millimeter, everything you have to vary gradually to actually get a clear picture. Right?
Sir, sorry to interrupt.
Yeah.
How did we conclude that all are important?
So we said that typically it is taken that something is, let's say, close to 1% or less than 1%. You say that, that parameter has negligible contribution towards the performance of the device or the system. Okay. But you can see that this is about 25%, this is about 15%, this is about 60%. So they are all relevant parameters. Okay.
Yeah, clear.
But what we learn from here is that the base thickness, that is the parameter B, is more crucial. Okay. So the most dominant parameter is XB, followed by XA, and which is again followed by XAXB, which is the interaction effect. Okay, so as I said, you can do this kind of 2 to the power k factorial design. Let's say you want to characterize, you have various parameters affecting your a particular experiment, right? So you want to do some experiment where you have certain output, right? Some certain outcome, and your outcome depends on, let's say, few variables, and you want to know whether all these variables are important. Do I need to gradually vary each of these variables to characterize my system or the device? Then what you do is you do preliminary experiment varying each of these parameters between, let's say, two extreme values, a low and high. So you get preliminary results. So that preliminary result is basically this matrix that we have. Okay. Now you can do a regression analysis, work with that preliminary results to arrive at a conclusion which parameter is important, which parameter is less important, and so on. So this will guide you in reducing the total number of experiments if that is possible.
Sir, I have a question, sir. Hello?
Yeah.
Thank you. Here you said that all of them are important, right?
Yeah.
But here we see that the dominant parameter XB has a significantly higher percentage share as opposed to the rest. So then with that comparison in place, how can we still say that all of them are important? I'm asking.
So I said
because
that all of them are important. Okay, that doesn't mean that all of them are equally important. Okay.
Okay.
So I also wrote that the most dominant parameter is XB. So that means if you really want to do experiment, your XB has a greater impact. That means you should vary with a smaller increment as compared to XA.
Okay. And sir, how are we identifying which will be XA and which will be XB here?
Yeah, so that depends on your, I mean, you can name anything, right? I mean, your model will basically take care of it. It doesn't matter really which one is XA and which one is XB. But what is important is this matrix, So if you can work through your matrix and you say that, okay, my XA, let's say you're doing some experiment and you have 3 variables, 5 variables, you can name them as XA, XB, XA, XA. This choice is yours, basically. I mean, it doesn't really matter which one is XA, which one is XB. But what is important is when you find these the sum square deviations, they have to be properly coded, right? And depending on your percentage contribution, you can really identify the dominant parameters, less dominant parameters, and so on. Or something may not impact at all, you can also determine those.
Thank you, sir.
Okay, so I have the remaining time. I would teach from a PowerPoint, so I have to really plug in this, and I have to stop sharing first. Let me just open the PowerPoint. Yes, is my screen visible to you?
Yes.
Yes, sir. Visible, sir.
Yes, sir.
Okay. So I wanted to talk about the orders of systems. Okay. First, we will talk about first order systems. So if you look at the various systems around you, the real world systems that we talk about, it could be any machine or an instrument. These are frequently represented in terms of simple models like the first or second order system, but you may have a complex system which can be decomposed into the simpler models such as first and second order system. So you can have one complex machine, you can divide into individual components which individually represent either the first or second order systems. Okay, so that means the higher order systems can be decomposed into first and second system. So it is important that we understand these first and second systems, which are the building blocks of the complex systems. So if you look at first order system and the response, these involve only real functions, as we will see subsequently. So this basically use only real mathematics. But as you see subsequently, the second order systems are typically have complex representation in their response. So if you look at a typical first order system, like let's say thermocouple, right? Thermocouple is a first order system. You have an input and you have an output. Okay, and depending on how the input varies, the output would have a characteristics which is of first order. Okay, so typically a homogeneous first order equation looks like this. As you see here, this is the typical first order system. Okay, here you have tau dy over dt. This is the rate of change of y with respect to time. Here y is a function of time, which is represented here, plus y as a function of time is 0. Okay, so this y can be anything. In case of a thermocouple, it is temperature, how temperature changes with time, right? So if you do an energy balance for a thermocouple, the final equation will come to this form. So here tau is basically a time constant of a system, and this is rate of change of y with time, and this is y that is equal to 0. So this is the typical first order equation. The solution to this equation, or the response that you get from this equation, is typically in this form, where y as a function of time is some constant c into exponential s into t. Okay, so where s is the frequency, s has a unit of frequency, which you can write as 1 over time constant also. Okay, so this equation will allow only one value of the frequency. Let's call that value be lambda 1, and which is a characteristic frequency of the system or the device that we are talking about. And this characteristic frequency is also known as the eigenvalue of the system. Eigenvalue is a characteristic value of the system. So in first order system, as I said, this frequency or the lambda 1 is a real number. Okay, but if you go to second order, you may have the frequency which is in complex representation. Okay, so limiting to first order system, the constant c is a real number, because if you look at here, this solution to the first order equation, if you take t equal to 0, let's say for temperature, right, you get temperature T varying with time as some constant exponential frequency time time. Now when time is 0, that is that initially this becomes 1, so your temperature will be equal to C. So this C will have the unit same as Y, just for dimensional consistency. So that is why it says that the constant C is a real number with the same units as y. Okay, it is used to set the value of the function at some point of time, typically at t equal to 0. So the value at t equal to 0 is called the initial condition of the response. Okay, so again we come back to the first order system, which is tau dy over dt plus yt equal to 0, and you get a response which is yt is c e to the power st. Okay, now first order systems, second order systems are important, because after this we are going to talk about measurement of temperature, measurement of pressure, flow rate, various kinds of different kinds of parameters. So when you talk about these measurements, knowledge of first order and second order systems are going to be important there, particularly when you are looking at the transient characteristics of temperature measurement, pressure measurement, and so on. Like for example, you talk about a thermocouple. So if you change the surface temperature from one value to another value, how quickly the thermocouple is going to record that change in temperature. Or let's say in pressure measurement, you are using, let's say, some kind of pressure transducer, let's say a simple U-tube manometer, right? And you have a change in the input pressure. So you're measuring pressure of a chamber and suddenly there is a change in pressure. How quickly your manometer or the pressure transducer is able to measure this changed pressure. Okay, so this is the dynamic characteristics. Okay, time dependent characteristics. In order to understand those, when we talk about temperature, pressure measurement in detail, knowledge of orders of system is very important. So that is why we are going through this math. Okay, so it will give you some generic idea about different kinds of systems. First order, second order systems are not only specific to temperature, pressure, and so on. They are generic. You can talk about even mechanical systems like spring mass dashpot system. It is a second order system. Okay, so you have to understand the orders of system. That is why we are going through this map. Now, coming back to the first order equation. So, as I said, a first order equation will have this form that you see here. And a solution to this first order equation will have a form something like this: sum constant times e to the power frequency times time. Now, if I substitute here, so this is tau. If you take derivative of y dy over dt, so you will have c into s into e to the power st. So this is this term, first term. Then the second term is just c e to the power st, that is equal to 0. Now if you take c e to the power st common outside this bracket, inside the bracket you will have ts plus 1, tau s plus 1. So basically, the first order system can be represented, if you this were to be the solution, it has to satisfy the fact that the time constant times the characteristic frequency plus 1 is equal to 0. Now for this to be valid, your s has to be equal to minus 1 over tau. Okay, so basically now the solution yt is c into e to the power, your frequency now you have found out is minus 1 over tau. So this is minus t over tau. So this is the solution to first order equation. Okay, so if you have any doubt, you please ask. Okay, I will stop and explain. Now, the response of a first order system typically is shown here. As you said, this is how the y is varying with time. Let's say in case of a thermocouple, this is how the temperature will vary with time. Okay. So typically in a first order system, the response will gradually decay to 0. Okay, as time increases, for the time constant tau greater than 0, if you perturb the system, it will gradually decay to 0 with increasing time. Okay, because first order systems are typically stable systems. Okay, and they would typically decay to 0. And here in this plot, as you see, this is time and this is your output. Okay, in a thermocouple, this is time and this is your temperature. So initially you have some temperature change that you induce it to, and so there is a step input that has come. Okay, let's call this as 1. Okay, so time t equal to 0, you have y0 is 1. Okay, now as time progresses, it will decay following e to the power minus t. So this is the characteristic of e to the power minus t. As time progresses exponentially, it will decay. Okay, now this decay would now depend on the time constant also. It will decay with time t, but it will also depend on the time constant tau that is at the denominator. For tau equal to 1, okay, this is the curve, tau equal to 1. You can see that when tau equal to 1 and t equal to 1 second, c is already 1. So your output will be basically e to the power minus 1. That is 0.37. So you can see here, when time t equal to 1 second, for tau equal to 1, the output has reduced from 1 to 0.37. Now if you go to 2 seconds, it will reduce to e to the power minus 2. that is around, let's say, 0.13 or something around that. Okay, that is basically 0.37 square. Okay, so and if you go to 3, it will be 0.37 cube and so on. Okay, here it will reduce to 0.37 cube, that is 0.05. And 0.37 is, I mean, this will be around, I think, around 0.12 or something like that, around that. Basically 0.37 square, whatever the value is. 0.4 is 0.16, so 0.37 will be around 0.12, 0.13, something like that. But if you use a different time constant, if you use time constant of 0.5, then the decay is going to be faster. Okay, but if you reduce the time constant, go to time constant 2, your decay is slower. That means the decay is faster for a smaller time constant. Okay, so when you design a thermal system, be it a thermocouple or any temperature sensor, you look for a smaller time constant of a system, because a smaller time constant system would be able to quickly detect the change that is happening in the input parameter. As the temperature is changing, if the time constant of your probe is smaller and smaller, it will detect very quickly. But if you use a time system which has long time constant, even if the change is happening, you may not be able to detect it. Okay, if the temperature is going from 50 degree to 52 degree and going to 43 degree, 56 degree, and every second, and your time constant of the system is, let's say, 1 minute, you are not able to detect anything. You need a temperature sensor which has a time constant much smaller than how quickly the temperature is fluctuating. If the temperature is fluctuating every 1 second, you must have a temperature sensor which has a time constant of 0.1 second, let's say, smaller than the time scale at which the temperature is varying. Okay, so this is very important to understand. Now, I think you also should learn how we can represent first order systems on a frequency diagram. Typically, we talk about this is in the time domain where the output is a function of time t. But these first order systems can also be represented in frequency domain. Okay, so from time domain to frequency domain, typically you can go by what is called Laplace transformation. Okay, Laplace transformation is typically used to convert a function that is in the time domain to a frequency domain. And typically this is used when you have complex partial differential equation and you want to convert, not solve this complex partial differential equation, but only solve algebraic equation. This Laplace transformation is powerful enough to convert the differential equation into simple algebraic equation. So in that way, Laplace transformation is very useful. But here, we just need to know that these response of the first order systems can not only be represented in the time domain, but they can also be represented in frequency domain. Okay, so in frequency domain, you have basically the real value of the frequency in the x-axis and the imaginary value of the frequency as the y-axis. Now, as we said, for a first order system, the frequency is -1 over the time constant. Okay, so and this has to be a real value, because first order system, the frequency has to be real value. If you take second order system, you may have imaginary values also. But first order system, it is since the solution is in real value, the solution will only lie in the x-axis, which has real values. And this has a negative sign. So since this is origin, the pole or the solution will lie in the negative x-axis, which is -1 over tau. And for smaller and smaller time constants, that means faster and faster systems, your pole, which basically is depicting this frequency, will go in the negative direction. So this is why it is saying decreasing tau. Decreasing tau means increasing the frequency, right? So that is going in the negative direction of the frequency axis. Okay. Now this is some very brief introduction to the frequency representation of first order system. We'll come back to it a little bit later. But before that, I want to introduce you to various kinds of signals. Okay. The first kind of signal is the impulse signal. Okay. You all know what is an impulse. You have a sudden jerk of signal coming over a very small time. Okay. So in this case, almost at an instant. Okay. So here you have x-axis, which is time. Y-axis is basically the input. And you can see this input is non-zero only at time t equal to 0. Okay. That means just at that instant, you have given an input. And then as time progresses, the input basically becomes 0. Okay. So this is known as an impulse signal. And if the value of this signal is 1, then you say that it is an unit impulse signal. Okay. Similarly, you can talk about step signal. Step signal is different from unit signal, from impulse signal. In impulse signal, you had a non-zero value just at t equal to 0. But in a step signal, you have the input as some a for time t greater than equal to 0. Okay. For the entire time journey, your value is non-zero. But if you go below time t equal to 0 and t greater than 0 is non-zero. But if you go time less than 0, t less than 0, the signal was 0. So this is basically a step signal. And if the step is 1, then you say that it is a unit step signal. Okay. In addition, you can also talk about ramp signal. So here, the ramp signal basically imitate the constant velocity characteristic of an input signal. That means as the time progresses, the value of the signal is increasing linearly. Okay, so that is what meant by constant velocity characteristic. Okay, like you talk about displacement versus time, your dx over dt is constant. That means velocity is constant. Here, your x is basically the signal, and basically dr over dt is increasing linearly with time. Okay. So dr over dt is a, that means rt is at. So your signal is linearly increasing with time for t greater than equal to 0, and it will be 0 for t less than equal to 0. And if the slope happens to be 1, the dr over dt becomes a, which if it is 1, then you say that it is a unit ramp signal. Okay. So this is as you go from time equal to 0 to 1 to 2, your signal becomes goes A at time t equal to 1 to 2A at time t equal to 2 and so on. And if A happens to be 1, then you name this as unit ramp signal. Then you have a parabolic signal, and this parabolic signal basically emitted constant acceleration curve. Okay. And typically the parabolic signal is given as A into t square by 2 for time t greater than equal to 0, and for time t less than 0, it is actually 0. And if A equal to 1, you call this as unit parabolic signal. So you can say that depending on t equal to 1 or 2 or 3, you will have, when t equal to 1, it is A by 2, so it's 0.5A. When it t equal to 2, it is 2A. Equal to 3, it is 4.5A, and so on. And when A becomes 1, you have a unit parabolic signal. So what is the relation between these different test signals we saw? So typically, so this is how you represent the impulse signal. This is how you represent the step signal. This is how you represent the ramp signal. And this is how you represent the parabolic signal. But these are related. Impulse signal is just at an instant. So if you time integrate it for time t greater than equal to 0, you actually get the step signal. If you integrate the step signal, you actually get the ramp signal. And if you time integrate the ramp signal, you get the parabolic signal. Similarly, if you take derivative of parabolic signal, you get the ramp signal. You take the derivative of ramp signal, you get the step signal. And you take the derivative of step signal, you get the impulse signal. So these are related. Okay, so I will stop here. And if you have any question, we would I'd be happy to answer.
Sir, how does the derivative of a parabolic signal represent the ramp?
Yeah, let me just show it to you.
Oh, sorry, the rate of change. Yeah, okay, I
Yeah,
can understand.
you take just the derivative, and you should be able to get that. You take derivative of this, and you get the ramp, and take derivative of that, you get the step. Okay.
Yeah, clear, sir. Can you just give a physical connotation for the parabolic changing to ramp?
Well, it is basically mathematical that if you want to know the rate of change of this signal, you would basically represent that by a ramp signal. Okay. So, and if you want to know the rate of change of this, you would basically represent that by a step. So it is really mathematical as such.
Okay, but
Yeah.
Sir, half sinusoidal signal or a very small frequency, if it is given, that also can be, in cases, can be considered as impulse signal. So, is there any methodology that we can differentiate?
Can you just 1 second? So can we stop the recording now? Because
Yes,
we
sir,
are
yes, sir.
discussing questions beyond the thing. So let me just.
Yes, sir.
How do I stop the recording?
Okay.
Recording stopped.
Yeah. So what was your question? Can you tell me?
Sir, half sinusoidal signal with very small frequency. So that will like just go as a ramp and means come back. Means
Any kind of
not-
signal, if you take
Yes.
over a very small time, you can approximate as a, you are saying impulse signal, right?
Yes, sir. Yes. Yes.
It doesn't have to be sinusoidal as such.
Okay, sir. So any means how we will differentiate means for the defining the time frame, that if it is there for based on the system response or the based on the equation, how we can define that this has to be considered as a impulse or not, sir?
See, again, I mean, you are going to be the best judge of that, because if your time, operating time is very long, right, compared to the time scale of the signal that you are talking about, because everything is a relative term, right? Impulse signals are really instant, right? It has to be an instant.
Yes, sir. Yes.
If your whole operating time is, a millisecond, and your signal is of the order of 0.1 millisecond, I don't think you can call it as an impulse signal unless it is of the order of microsecond or nanosecond. So the point I'm trying to make here is that depending on your operating time window and the signal width, you can decide whether it is an impulse or a finite signal. Okay.
So it has to be ultimately decided by the.
Yeah, I don't think there's
architect.
any hard and first rule as to, okay, this has to be called impulse signal and this has to be called a finite signal.
Understood, sir. Thank you, sir. Thank you so much.
Hello, sir.
Yeah.
When we were discussing about the definitions, this zero can be a minima also, right, sir?
With regards to what can you say?
In the slides, we have 0 and A, right, in terms of impulse.
Yeah.
That 0 can be a minima also, right, sir?
In which signal you are talking about?
In any signal, sir.
So
I think what he's trying to ask is the starting point can be the minima point of any.
it can be. I mean, that's not the point what we are discussing here. Here we are saying that, depending on which signal you are talking about, I mean, how we define the signal with respect to the time, right? So, I mean, 0 can be the minima as well.
It would depend on the instant that we're talking.
Yeah, it would really depend on the time instant that we were talking about.
Okay.
So, I mean, see, the value of A can be negative also, right? So
Yes.
that is not what we are really talking about, minima or maxima here, but we are more worried about the characteristics.
Understood.
All right. So if no further question, we'll meet again tomorrow.
Yes, sir.
Thank you very much.
Thank you, sir. Thank you, sir. Thank you so much, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir, so much.